Okay, so I'm going to introduce you to the topic of power analysis. You may recall that in first year you learnt that if the p-value is not significant, we cannot conclude anything about the data. That is, our conclusion is there is insufficient evidence to make any conclusions about whether there is a relationship or a difference in the population. This year we're going to learn something a little bit different, and this depends on power analysis. You need to conduct a power analysis whenever the correlation is not significant. This will allow you to determine whether the non-significant finding is due to insufficient evidence, as you learnt last year, or alternatively, whether it is because there is little relationship in the population to detect in the first place. If your power analysis shows that there is sufficient power, we can conclude that the sample did not detect a correlation in the population because the correlation in the population is very small, negligible, or weak. If our power analysis shows that there is insufficient power, we can conclude that the sample provides insufficient evidence about the population to allow any conclusions, just as you learnt last year. So, whenever the sample correlation is not significant, we perform our power analysis. Power analysis depends on sample size, but sample size in turn depends on three other factors. These are the strength of the correlation that you want to be able to detect, how confident you want to be about detecting it, and the level of significance you are going to test at. So in this unit, as is very common, we will test at a p-value of 0.05, alpha equals 0.05. We are content with an 80% chance of being able to detect the correlation, and we are content with being able to detect correlations of 0.3 in the population or stronger. Correlations that are weaker than 0.3 tend to be uninteresting anyway because they are so weak. So we are happy to just be able to detect correlations of 0.3 or stronger. So ideally you should conduct the power analysis before collecting the data. So you need to ask yourself how many participants would be required if we wanted to have an 80% chance of detecting correlations of 0.3 or stronger, and we were testing at the 5% level of significance. So you go to the power table in the back of your textbook for correlations. These power tables are all calculated for a p-value of 0.05. You find a correlation of 0.3 because we're happy to be able to detect correlations of 0.3 or greater. You find that column of 0.3 and then you find the 80% power row, and you can see that we need to have 85 participants to be confident of detecting a correlation of 0.3 with 80% power. So what if the data has already been given to you? We've already collected the data and we want to know in retrospect, was there sufficient power? So we find the correlation is not significant, and we need to decide whether this is because there is insufficient evidence, the sample doesn't tell us enough about the population, or whether there's a minimal relationship in the population to detect in the first place. So the only bit of information we need is the sample size, which in this case is 200. So again, we go to the power tables in the back of our book. We can see the correlation was not significant, and we need to ask if it's powerful or not. So we go to the power tables in the back of our book, and we go to the 0.3 column again because we want to be able to detect a correlation of 0.3 or more. We look up sample size of 200 and we can see that we have 99% power. We have 99% chance with 200 participants of detecting a correlation in the population of 0.3 or greater. So the fact that there was no correlation despite having 99% power suggests that the correlation in the population is minimal. So the study was sufficiently powerful. With a sample of 200 participants, we had 99% chance of detecting a correlation as small as 0.3, and in fact we had an 81% chance of detecting correlations even as weak as 0.2 if you go to the 0.2 column in your table. But we didn't find anything, so we can be confident that if there is a correlation in the population, it is extremely weak. So you write your report as usual, and you conclude as usual. There is insufficient evidence to suggest that students who complete more revision exercises tend to get a higher exam mark, And then you add that a power analysis indicates that there was a 99% chance of detecting a correlation as weak as 0.3 if one exists in the population. So we can be confident that if there is any correlation in the population, it is only weak. Okay, so that's an example where there is sufficient power. Let's have a look at an example where there isn't sufficient power. So in this example, again, we have a non-significant correlation, and we only have a sample size of 20. So we go to our power tables. The correlation was not significant. Was the study sufficiently powerful? If there's a correlation of 0.3 or stronger in the population, how much chance do we have of detecting it? N equals 20. So we go to our correlation table in the back of our book. We look up a correlation size of 0.3. We look up 20 participants, and we can see there was only 25% chance of detecting a correlation of 0.3 or more with only 20 participants. So the study was not sufficiently powerful. We didn't have at least 80% power. With a sample of 20 participants, we only had a 25% chance of detecting correlations as small as 0.3. So the study should be repeated. Hence, we write our report as usual. There is insufficient evidence to suggest that students who complete more exam revision exercises tend to get a higher exam mark. And then we add, a power analysis indicates that there was only a 25% chance of detecting a correlation as weak as 0.3 if one exists in the population. Full stop. The study should be repeated with more participants. And that is the end.